Hello friends, I am Dr.V Deshpande, Head Department of Physics, Shivaji College Kannad. Now this is interaction of electromagnetic waves with matter. Before discussing the behavior of electromagnetic waves at the boundary, we will find the boundary conditions holding at the surface of discontinuity between two media. Now boundary conditions for the electromagnetic field vector at the interface between two media. While solving the electrostatic and magnetostatics boundary values problems, an important role is played by the conditions connecting the electromagnetic field in different dielectric media. Now, boundary conditions for the electromagnetic field vector B. Consider the pill box. This is pill box structured situated at the boundary interface between medium 1 and medium 2. This is medium 1, this is medium 2, and this is pillbox. As shown in figure, S1, S2, S3 and S4 are the surfaces of pillbox. This is S1, S2, this is S1, S2, S3 and S4. These are the surfaces of this pillbox. H is the height of pillbox. N is the normal vector to both medium. Also the surfaces S1 and S2. A represented the area of S1 and S2. We know from Maxwell's second equation divergence of B is equal to 0 or del dot B is equal to 0. To calculate the effect of magnetic field over the entire volume of pillbox as shown in figure, let us take the volume integral on both sides of the equation. That is volume integral of divergence of B into dV is equal to 0. Now volume integration is converted into surface integral by using Gauss divergence theorem. Therefore, it is integration over closed loop B dot ds is equal to 0. So integration over all the surfaces for the figure is for surface S1 it is integration over S1 B1 N1 ds plus integration over S2 B2 N2 into ds plus surface S3 B3 N3 into ds plus integration over S4 B4 N4 into ds which is equal to 0 as H tends to 0, that is height tends to 0. This is conditions. Then third and fourth integration becomes 0. Therefore integration over a b1 n1 plus b2 n2 into ds which is equal to 0, where s1 is equal to s2 is equal to a. Since surface is arbitrary non-zero, therefore b1 n1 plus b2 n2 is equal to 0. Since normal vectors n1 and n2 are opposite directions, we can take n1 is equal to n and n2 is equal to minus n. So equation becomes b1n minus b2n, which is equal to 0. That is, b1n is equal to b2n. This shows that the normal components of magnetic field B is continuous across the boundary interface. Now consider second condition, that is boundary condition for electromagnetic field vector E. Consider the interface between two media. Construct a rectangular loop ABCD bounding a surface S as shown in figure. Now Maxwell's third equation is curl of E is equal to minus of dou B by dou T. Now integrate this equation over the surface S of loop ABCD so as to find continuity for electric field component E. Surface integral of del cross E dot n into ds, which is equal to surface integral of minus of dou B by dou T into n into ds. Now using Stokes theorem, convert surface integral into LHS into line integral, that is integration over closed loop ABCD E dot dl is equal to minus of surface integral of dou B by dou T into ds, n into ds, which is equal to integration over AB E1 dot dl plus integration over BC E dot dl plus integration over CD E2 dot dl plus integration over dA E dot dl, which is equal to minus of surface integral of dou B by dou T into n into ds, where E1 and E2 are tangential component of electric field in the two media. If S tends to 0, then contribution from line integral over BC and dA will tend to 0. And also surface integral on RHS of equation is also 0 provided dou B by dou T is everywhere finite. So integration over AB E1 dot dl plus integration of CD E2 dot dl is equal to 0. Integration over AB E1 dot dl minus integration over DC E2 dot dl is equal to 0, as direction of AB and CD are opposite. Therefore, E1 of T minus E2 of T into L, which is equal to 0, since L is arbitrary non-zero, that is E1 T minus E2 T is equal to 0, that is E1 T is equal to E2 T. This shows that the tangential component of E must be continuous across the interface of two media.